Great, thanks for the opportunity to speak today. This will actually be a two-part talk. I'll be talking first about the computational aspects of the project, and after this, Dan Jacobson will give a talk on the science motivation and science applications of this work. Okay, this talk is going to be about taking comparative genomics algorithm and mapping these to unconventional hardware, in particular mixed precision hardware. We've heard a lot about growth in mixed precision in the last couple of years since it was discovered that deep learning algorithms can perform effectively with lower precision arithmetic and give comparable results at higher computation rates. In fact, the IEEE Computer Society gave their top 10 list of top trends for 2019, and number one on the list was deep learning accelerators, which is kind of interesting. And we are also, of course, seeing this in the vendor space. Different vendors, NVIDIA has announced 2 years ago at NVIDIA GTC, they announced the Volta V100 with 120 to 125 teraflops performance for the tensor cores. There's been various terms have been used for this. It's not a true HPC double precision floating point operation, but other people call it ops, flops, ops, or some people call them AI ops to distinguish these from the true, the full precision, double precision arithmetic. So more recently, the Turing, NVIDIA Turing architecture and T4 GPUs, AMD with their Radeon product line with the MI60 accelerators. Google has their own custom processor, tensor processing unit, which has gone through a couple of generations. Other vendors as well, and by one report, as many as 45 to 50 startup companies developing special purpose deep learning accelerators, some with precision as low as single bit. And these obviously can offer a tremendous potential performance boost. The NVIDIA Tensor Cores half precision on the Volta architecture is 16 times faster than the double precision corresponding operations. And to put this in perspective, it's kind of interesting to observe that if you look at the ORNL Titan system, which is being decommissioned this year, it's the first multi-petaflop GPU-based system. Basically, the GPU to CPU flop rate ratio for that system is about 10 to 1. So the old K20X GPUs are about 1.3 teraflops double precision, but the CPUs were about 140 gigaflops. So to be able to exploit these, this mixed precision unit that's on the die is could be as effective as porting to a GPU and getting accelerated performance. That is, if you can use the reduced precision for your application. And indeed, some people are trying to do that already. 4 of the 6 Gordon Bell finalists this last cycle from last November used the tensor cores on CoMet for their work. And so it's generating interest. Other application teams and library developers are looking, how do we use this effectively to speed up our applications? And in this talk, I'd like to talk about the CoMet code as a relatively new application and describe how on CoMet we have accelerated this with that hardware. Just a quick review. Everybody's familiar with this material already. The overview of CoMet. It's basically was officially launched last June and deployed for general use by its users this last January. It's currently the fastest, world's fast supercomputer. The nominal peak performance is approximately 200 petaflops. But if you look at the half precision and tensor cores, it's really a 3.2 exaops mixed precision system. It's number one on the top 500. The latest number was 143.5 petaflops. Also number one on the Green 500 list for power efficiency, and also number one on the HPCG benchmark, which was described in an earlier talk. Also, it was used to perform the first exaop calculation by an application, the 2.36 exaops, and it's already generating new science for the 30-plus DOE Insight projects, which are using the system, as well as other projects that are using the system. Just a quick look at the system architecture. On the right here, 256 compute racks, total of 4,608 compute nodes connected with a Mellanox InfiniBand fat tree fabric and runs at 13 megawatts. And on the next slide, there's a more detailed diagram of the node architecture. The node contains two IBM Power 9 CPUs. Here they're connected to the DRAM for half terabyte of DRAM on the node, and also connected to the 6 Volta V100 GPUs. They have their own on-package HBM memory, and also it's connected, of course, to the NIC and connected to the Mellanox InfiniBand interconnect. It's also connected to an on-node NVMe device for fast I/O and added storage, and also the nodes are connected to a GPFS file system. So we want to use CoMet to solve comparative genomics problems. I'd like to describe what those problems are in a little detail. We'd like to find in this project the genetic causes of individual traits that manifest in individuals. For example, it might be a susceptibility to some disease, and Dan will talk about this in detail in his talk. These traits are sometimes caused by a complex interplay and interaction of different elements in the genetic material, and it's unknown beforehand which of these elements are interacting to cause these traits. So this is exactly the kind of problem we want to solve. We don't know a priori what they are, and so we have to look at combinations of these traits to see whether they're co-occurring and associated with the manifestation of a trait. So this is a huge combinatorial problem, very, very difficult to solve computationally. And what the methods we use are basically vector similarity search to find the clusters of vectors, each vector associated with a specific genetic feature, the clusters of vectors that are self-similar, similar to each other. And this has a high computational complexity for vector length n, m vectors of length n, cluster size k, its order n to the km, so exponential in cluster size, and because it's exponential, really k has to be limited for our work, so we really only look at two-way and three-way interactions in this work because of this combinatorial explosion of the relationships. And not only does it require a lot of computations, but also because this is an all-to-all computation, it requires a lot of communication, therefore a lot of network traffic, very large messages all being exchanged at the same time. So it's very also taxing to the interconnect. So what is our approach to solving this problem? It turns out that vector similarity search is very similar to a known problem that we've looked at in the community for actually decades. Identical computational pattern to the matrix, dense matrix product, which is known to the library developers as a GEM, General Dense Matrix product, has identical computational pattern. And the advantage is that GEMs have been studied for a long time. They're well understood, and also there are significant libraries that have been optimized for different hardware platforms. This example being NVIDIA cuBLAS and Intel MKL libraries. Pretty much any new HPC system has to have a highly performing GEM operation from a library. These libraries are specifically optimized to the memory hierarchy of their respective processors, the use of the caches, the different levels of caches, scheduling, register usage for optimizing the computation part, and so on and so forth. And because these libraries have been developed, we can leverage these to perform these calculations. So I don't want to get too much in the weeds in the talk, but mention very quickly what some of the methods are that we need to implement for this work. There are two main methods. One is called a proportional similarity metric. The computation is very much like a GEM, but whereas a GEM calculation is based on an FMA, fuse, multiply, add operation, instead the proportional similarity metric has an operation here that is based on an add and a minimum of scalars operation, taking the minimum value of 2 given floating point numbers. So this is not commonly implemented as a fused add and minimum in hardware. However, very commonly this minimum of scalars is implemented on hardware by itself and on modern processors and on GPUs. So this can be exploited to advantage to speed up this calculation. And the second method is a custom correlation coefficient. It's a different kind of method. It doesn't operate on floating point data. It operates on binary data. In particular, binary data that encodes the allele information in the different genomes that are being run. It essentially counts occurrences of joint relationships between the vectors being compared. And in this case, we're doing a counting of bits, and it turns out we can use a population count operation, which is also commonly implemented on some CPUs and on GPUs as well. So this is very helpful in implementing these algorithms and getting higher performance out. So how do we implement the first method, the proportional similarity method on GPUs? Essentially, we take advantage of an existing library, the Magma linear algebra library developed by the Innovative Computing Laboratory, Jack Dongar's laboratory at UT Knoxville. We essentially modify that code, particularly the gem kernel in that code, to implement this operation. In a conversation with Stan Tomoff in the group, Stan told me that this is not uncommon for them from time to time, either end user or with their help, to implement some custom operation by adapting their code. And this is exactly what we do, and take advantage of the CUDA intrinsics, fmin, fmin-f, which map to hardware operations on the GPUs to give really high performance. And insofar as the memory traffic has already been optimized by these libraries, we're kind of left to the bare metal of what the compute itself can do apart from the memory access. And here, that's why it's very critical to get as high compute performance as possible. And the second method here, a triple C method, we use a similar approach. We also use the Magma library. We take the binary data, pack this into 64-bit words, use various bitwise operations that are on the processor, and the CUDA intrinsic for population count gives a very fast computation for this operation. So this was the original method. Since the tensor cores came out, looked at this a little more carefully and found out there's actually a way to use the tensor cores. Tensor cores are actually very restrictive so far. They can only implement matrix products, not general floating point operation, but always just a 4x4 matrix product. So how do we sort of shoehorn an existing operation into this? Sometimes takes a little thinking, and came up with a mathematical trick to represent the matrix containing the vectors, represent this as an FP16 matrix of larger size, and use the tensor cores, giving the exact same bit-for-bit operation as the original method with no loss of accuracy. And so we found a way to use the tensor cores. They were really just developed by NVIDIA with deep learning in mind, but we as scientists want to see, well, we've got a new hardware. How do we use that? So we want to explore that. In this case, we found a way to do it. And one other aspect of the implementation, it doesn't do us any good to get higher performance on the CPU if we can't also take care of the required communication for the algorithm. And so how do we actually run this, not on a single GPU, but on thousands of GPUs? Summit has over 27,000 GPUs. And the approach we use follows an existing library, the Scala-Pack library, with parallel BLAS underlying library. We essentially take the matrices, decompose these by row and columns to get blocks. These blocks can be distributed to the GPUs and the computation performed. But it's extremely important to use asynchronous transfers to and from the GPUs and asynchronous communication to hide all this heavy communication underneath the computation. And in fact, really the tensor cores are so fast that we start to kind of reach the limit of what we can do, because now the computations have accelerated so much that we're starting to see a little bit of the impact of the communication and transfers. So now I wanted to move on next to some results. This slide presents a scale-out study on CoMet to pretty much the whole system. And there are a lot of different methods and method variants here. Here the y-axis is the time in seconds, and we keep a fixed amount of work per GPU, so it's a weak scaling study, and measure the wall clock time. And basically all the methods give us near perfect weak scale out to like 99% of CoMet. And this is made possible by sort of the amazing fat tree network with adaptive routing on CoMet. We get pretty much congestion-free communication. This communication pattern is pretty much exactly the same as the MPI graph benchmark, which is doing exchanges between all nodes at the same time with large messages. And those benchmarks show like near perfect performance up to the full CoMet system. So it's very much to advantage that we have this network on CoMet. Titan 3D Torus was not always as congestion-free as this. It's a definite advantage. And performance, the full system performance, there are a lot of different methods here, but just want to point out this method that used the tensor cores. We're getting 2.36 exaops of performance, which is about 75% of the peak mixed precision performance of CoMet. And in fact, this number is actually slightly a little higher fraction of peak than is achieved by the HPL benchmark for the top 500 number. We're getting 86 teraops per GPU, and the advantage we're getting from the tensor cores, it wouldn't help if the actual time to solution were improved. We're actually getting about a 4x performance improvement compared to the bitwise method from use of the tensor cores. So in a sense, we're already achieving sort of exascale class performance. However, we won't get really true exascale performance broadly applicable to all science applications until we get the new systems like Frontier, Aurora, and El Capitan in like the 2021-22 timeframe. But now we're able, at least for one application, to sort of get the qualitative types of results that we could expect from exascale. This slide gives a comparison to state-of-the-art methods. Really, there's been no effort previously to run an algorithm like this on a large, very large HPC system with GPUs. Though there have been a few efforts to run on GPUs and some efforts to run on non-accelerated systems. The fastest known two-way method was run on 512 nodes of Edison, and basically we're 21,000 times faster than that. And there's not so much work in the literature on three-way comparisons, taking 3 vectors at a time. The best one we could find was on 4 NVIDIA GPUs, and we're 300,000 times faster than that. So we're getting basically 4 to 5 orders of magnitude faster than state-of-the-art. And this, as I said, it's basically because no one has ever tried to run this on a system with thousands of GPUs before. So this has very much helped us to implement this on GPUs. And this slide is performance on a real-world problem. We collected a data set with human genome data set, a vector length of 600,000 with 81 million vectors, and ran this on 2/3 of CoMet. The run took for the whole data set, the two-way method, it took 3 hours. Interestingly, about 89% of the runtime is spent in the algorithms I've described in the previous slides. Only 11% was spent in I/O and overhead. So we're getting, even for a full application run, the whole thing with I/O and overheads, we're getting a really, really good performance. And point out that if we looked at the next highest comparable state-of-the-art, running this 3.3 hour job would have taken 15 years of wall clock runtime. So we can really address some problems we've never been able to address before with this. I want to conclude with some kind of thoughts and questions and ideas here. related to this work. So first question is, okay, we've used reduced precision for this application. It's not a conventional HPC application solving PDEs, which a lot of us are used to doing. It's a data analytics application, really. How can we apply reduced precision to benefit with a broader range of applications? And we're having many discussions right now at Oak Ridge and with other colleagues about how that can be done. But as soon as we started looking at FP16, we see that there's even lower precision coming. The NVIDIA Turing architecture tensor cores implement integer 8, integer 4, and even integer 1 single-bit gems, if that can be believed. It's kind of mind-boggling. Can we use this for any purpose? Are there any apps that can use these? Because if they could, it could be a huge performance improvement. Another question is, well, Tensor Core has a fairly restrictive operation, 4x4 matrix products. It is possible to generalize this so that other applications could take advantage of faster reduced precision. A more general issue is that we're kind of facing a compute jungle now. We're getting, we thought we were kind of like started on this road on GPU computing in 2009, and well, we thought this was hard enough to bring. We thought there was some stasis in the business where we have like an accelerated node that was sort of converged, but now we're seeing more heterogeneity come into the nodes and the processors. How do we take advantage of this? Vendors are putting this in. How do we use it? Can we use it? And how do we use this in a performance portable way for our codes to alleviate the maintenance burden, which all developers are concerned about? How do we maintain these codes? And finally, we've continued over the years to see this growing gap between higher and higher flop rates on the processors, and the memory and interconnect bandwidths are increasing, but not as rapidly. We had a real improvement with the HBM memory. That was very advantageous. But still, there's kind of seems to be a stress point. It's causing some algorithms to really not be usable anymore. If this trend continues, how will our codes adapt to this changing system balance that we're seeing? So just some conclusions. We found a way to use the GPU tensor cores to map this data analytics application. Tensor cores gave us a 4x performance improvement compared to the previous implementation, and we'll now be able to solve some really large and difficult problems that we couldn't think of before. And this highlights our need to continue to optimize our algorithms to get high computational intensity. A lot of people are doing this for different algorithms. For example, Exascale Co-Design Center to find on the SEED Co-Design Center to look at discretizations to try to get more high computational discretizations for solving PDE problems. So we need to increase computational intensity in order to take advantage of more powerful processors. And also the general aspect of this is we just need to do whatever it takes as scientists, computational scientists and developers to take advantage of the new kinds of hardware that the industry is giving to us. And we are definitely looking for more ways to exploit this at the OLCF. So I wanted to just thank my colleagues who are been involved in this work, and also thanks to the team for the accomplishments. The first exaop calculation by an application, and also the Gordon Bell Prize last November. So I'll take any questions people might have.